recall that in the last video, we started moving ourselves away from thinking about individuals, individual die rolls for our particular example, but it could work for individual anything, individual students, individual scores, etc. And we're going to walk away from that a little bit. That's what we were working on basically up till chapter 7. And now we have to make a big leap, conceptually speaking, into starting to think about samples. So we want to think about, hey, if I take samples of size 2 or samples of size 6, how do they compare? How do they vary from sample to sample? And we'll have to look at specific numbers from sample to sample so we can measure that. And the first number we're going to look at in section 8.1 is the mean. So how do the means compare when you take a mean of a sample versus the mean of another sample versus the mean of another sample? How does that distribution work? All right, so we saw that what was happening is, first of all, when you take samples versus individuals, you start getting a normal distribution, and the spread gets smaller and smaller and smaller the more that we do this, right? The larger your sample size is. All right, so we want to formalize that into one of the most important theorems in statistics, which is the central limit theorem. And theorem in mathematics, well, they're very important, but it basically means a statement of theory that we can back up with evidence as long as we take the mathematical structures to hold true. So as long as things work like we think they will, then this theorem will hold true, roughly. All right, so suppose that there is a population of size capital N, and that population has a mean mu and a standard deviation sigma. Now notice we're using the Greek letters there because this is for a population, right? So you hypothetically know your entire population. And then you're going to draw from that population a sample of size little n. All right, now what are some conditions that we have on drawing that sample? Well, there's one big condition which is pretty common for our course, which is that the sample that you draw must be random, right? So every observation that you collect must be random from that population. You can't bias your samples. That's different from sampling error. Sampling error is just that every sample is slightly different, right? But sampling bias means you've messed up how you actually draw the sample, and that's not good. Condition number 2 is that when you draw these samples, they must be independent. Actually, the observations within them must be independent of each other. Now, if they're collected with replacement, then this is no problem, right? When you take a die and you pick it up in your hand and you just start rolling it, you have independence because dice are independent. Roulette wheels are independent. Lotto number drawings are independent, things like that. If you're not going to collect it with replacement, if you're going to collect without replacement, so imagine you're going to reach into a large bag of M&Ms. When you pull the M&Ms out, they will be, hypothetically speaking, a random selection, but will they be independent? And the answer is no, because when you draw those M&Ms out of that bag, you're affecting what's left in the bag. All right, so when you do that, and that also works, by the way, for drawing people from a population. Let's say you're calling people up to ask their opinion about something. Well, you do that without replacement because you don't want to replace the people. That would mean you talk to the same people more than once. That's no good. So when you collect a sample without replacement, in order to ensure independence, you have to make it so that the sample you're drawing is at least, or excuse me, the population is at least 20 times larger than the sample size. In other words, your sample size is less than 5% of your population size. Now, what in the world is that talking about? Well, imagine your M&M bag. If you get like a small bag that you buy at the gas station, when you take 20 M&Ms out, or 30 M&Ms, let's take 30. So you take 30 M&Ms out, you're really affecting what's left in that bag, right? But now imagine you go to the factory and there's a vat of M&Ms, and you reach in and you take 30 at random. Well, have you really affected what's left? And the answer is yes, technically, but the vat of M&Ms is so large, more than 20 times larger than your sample, that it doesn't really matter, right, that you did that, right? I mean, yes, it matters technically, but it's not enough for us to worry about. And so that's what this is saying. So if you're going to do this without replacement, so imagine drawing a card from a deck or drawing M&Ms from a big bag, something like that. It has to be a huge bag. So when you take your M&Ms, you're not fundamentally affecting what's left. All right, then normal. So we need the distribution to be normal, and we're going to ensure this one of two ways. One, if the population distribution is normal to begin with, then we're golden, right? Then everything's normal. So it'll be given to you in the problem, or you can see it in a normal probability plot. It'll be normal, and you'll be like, great. If it's normal for sample size 1, it's normal for sample size 2, sample size 3, everything. If it's not given to you that it's normal, however, we want our sample size to be, quote, large, end quote. Now, we can finagle with this a lot, but our rule of thumb for this course is going to be greater than or equal to 30. So as long as it's greater than or equal to 30, we will say that's roughly normal shaped. All right. So if we have these three conditions met, if we've taken a random observation, if the observations are independent of each other, and or when you collect with replacement, or excuse me, without replacement, then your population was just so huge that your little sample wouldn't affect it that much. And either it was given to you that a population was normal, or you have a large sample size. Once you have those three conditions, then the following will be true. Your distribution of your x bars, your sample means, will have the following shape, center, and spread. The shape will be approximately normal, no matter what the shape of your population was. So if your population was skewed right and all kinds of crazy stuff, as long as your sample size was 30, you're great. If your sample was normal to begin with, then you're still great, right? So either it was given to you that it was normal, or you get n to be larger than 30 and it's normal, larger than or equal to 30. Then the center is the mean, which is mu sub x bar, which is mu, right? Your mean. Well, that's pretty easy though. If the mean is what the mean was to begin with, hey, nice for us. But what really matters is the spread. All right. So the spread will change. Instead of working at standard deviation, right? Standard deviation, raw standard deviation is talking about how individuals vary. We're going to talk about the standard deviation of the sampling distribution of sample means. And that is just a ton to say. So mathematicians are like, let's not call it that because that's too many words. We're going to call it the standard error of the mean, or SE of x bar, or sex bar, if you want to abbreviate that way. Set the standard error SE of x bar. So that's what standard error is. It's how samples vary from sample to sample, or excuse me, how the variability from sample mean to sample mean to sample mean, if you will. So it's sigma with a little x bar or sex bar, and it's got sigma divided by the square root of n. All right, now this is a lot to keep in mind. So let's look back for a second, what we were seeing here. So we started off with a distribution that was not normal. See this? This was uniform. It had a center and it had a spread. And what we were seeing is as we took samples and graphed the means of those samples, it became kind of bell-shaped. And the center was still 5.5, right? That didn't change, which is what the theorem says. The center is going to stay around what it was. But the spread is going to get smaller and smaller and smaller because you're dividing by the square root of n, right? So that's why 6, when n was 6, had an even smaller spread than when n was 2. And that's what we were seeing down here in this picture right here. Let me go back. Oop, down here. All right. So now that we understand this and we say, okay, averages are different from sample to sample, but they'll make their own distribution. The distribution will be normal. It'll have a center that was the mu. It'll have a spread with this formula right down here, which is your buddy and pal. You need to have that one known, okay? Or put it on your note sheet. That's fine. So if that's the case, then let's go back and look at those graphs, the graph that actually had the 2 and the 6-sided dice together, and let's figure out the mean and the standard deviation for each of those. So back here, just right, we went too far. This one right here, that had a mean of 5.5 for both of them, but it had a spread. Now let's see here. So like magic, I just typed him in. So let me see if I can show you how I came up with it. So n is 6 for the gray one. Remember we said that earlier because it is a larger sample, so it's going to be more squashed in. And now we can see exactly how much more squashed in because I found the standard error to be that. Now how do I do that? Well, the standard error formula says it's sigma over the square root of n, right? So sigma, if you recall, was 2.872. It's right back, right there, 2.82. So, sorry, if I take 2.82, which I'm realizing now I should have done all along here. These should be 2.82. Sorry, my fault. 2.82. There we go. Okay, so if it's 2.82, then I'm going to take 2.82 and I'm going to divide by the square root, so second square root, right there, that button, of 6. Enter. And I get 1.151. Oop, I went too far. Seriously. Actually, I just went to double check myself and I was wrong. It was 2.872. So that's a typo right there that I'm gonna have to fix in the notes. Sorry. It's 2.872, which is what I used for these other values right here and right here. So I need to take 2.872, sorry, 2.872 and divide it by the square root of 6. Yep, and that's the 1.172 that I see right here. See the 1.172? And now I want to take 2.872 and divide it by the square root of 2. Enter. And that's the 2.031 that we see right there. Wonderful. Okay. So we can see that the theorem is holding up, right? So the center is what we expect. They're both normally distributed, and the standard deviation has turned into something called the standard error. It is smaller than the standard deviation was. The standard deviation was 2.872, but the standard error of this sample mean is smaller than that. And the larger your sample it is, the smaller it is, which is, I believe, the next point right here. Okay, so as n becomes larger, our shape becomes, well, more normal. If it wasn't normal to begin with. How about this? How it becomes normal as long as n is greater than or equal to 30. There we go. The center becomes mu. Well, I mean, it was mu anyway, but it's even more so mu. So that doesn't change no matter how large your sample size is. So it stays consistently at mu. Okay. But the spread, now the spread is another story, right? The spread will shrink. And the larger the spread, or excuse me, the larger the sample size, the smaller the spread. Because n is in the denominator, right? The square root of n is in the denominator. So that means that the larger your n is, the smaller that the overall fraction is, i.e. the smaller your standard error is. There we have it. So just to recap, n becomes larger, n becomes larger, your shape is normal or it becomes normal to begin. It's either normal to begin with or it becomes normal if your n gets large enough. Your center is at mu, the center, mean, and then your spread gets smaller and smaller and smaller, and it turns into standard error sigma over square root of n. Right? The larger your n is, the smaller your spread is. Right? Everything else is pretty consistent, namely the shape in the center. All right, and then this is what I was explaining earlier. Why does n less than or equal to 0.05 capital N imply independence when sampling without replacement? And that's because your sample is so small compared to your population size that taking your little sample out doesn't really materially affect what's going on. So let me type that up 1 second. There we go. If your sample size, little n, is less than or equal to 0.05 capital N, your population size, that means that your sample size is so small compared to the population that when you draw the sample out, you have not significantly affected the rest of the population, right? And the example I give is the M&Ms, right? So if you imagine yourself drawing a small bag of M&Ms from a huge warehouse, like, go to Costco and get a giant bag of M&Ms. You draw that little sample of 30 out, you're not really fundamentally affecting what's left. I mean, you are at its most basic level, but it's so small that you basically can ignore it. And upon this, many children have snitched candy, right? So children run by this principle all the time. They're like, if I just take a little bit, they won't notice it. That's what they're doing, right? So they're assuming a certain amount of independence, that the parents won't notice that they're snitching candy if they take a tiny enough amount. And that's essentially what we're saying here. But for populations, I should say. So imagine, instead of candy, imagine that those candies are standing for people of different races, creeds, genders, etc. So when you grab, the color orange, you're grabbing, I don't know, Native American people, or when you grab the color yellow, you're grabbing, women, that kind of thing. And so when you do that, if those colors represent different things, then that's the same thing as having the big bag represent the huge population you're drawing from, and the different colors are the different aspects of the people that you're interested in.